Hi, welcome everybody. Yeah, I'm Markus. I work on TLA Plus, have been working on TLA Plus for about a decade now, both in terms of telling people how to use TLA Plus, but also on the tools we have to check the specifications and so on. And there are a couple of recordings of mine on the internet. There's one for this particular talk here. It's kind of the movie theater version of it, condensed to 40 minutes. But today we have a bit more time, so we can go into more detail. And the problem we are going to study with TLA Plus is a blocking queue or producer-consumer reader-writer problem. I'm pretty sure all of you have implemented it once. Oh no, we don't want the. Let's see if we find the right slide deck. It's this one here. So we have a number of processes or threads, whatever you like to call them, who are our producers, who add elements to this buffer here. Okay, and the buffer is of a fixed size, doesn't grow or doesn't shrink. Once it's full, no new elements can be added. If it's empty, you can't remove elements. The C's over here, our consumers, they remove the elements, right? So producers add elements, consumers remove elements, and everything is kind of synchronized, and there are no data races whatsoever. But for some reason, after a while, whoop, too fast, it can happen that there's a deadlock, okay? And I'm pretty sure that some of you, during your whiteboard interviews, were asked to implement the reader-writer problem in Java. But before we go into the problem, let me just give you a super high-level introduction of TLA Plus, what it is, what it tries to do. So TLA Plus is a specification language, okay? So the warning is here, you don't execute a TLA Plus specification. You write a TLA Plus specification to get a very good understanding of the problem, so that once you go and start writing the implementation, you know what you're doing. Okay? Typically, we prototype, yeah? And then we learn a lot while prototyping, but also writing prototypes is a lot of work. And typically, we end up shipping our prototypes because we ran out of time of doing it over again, right? So the idea of TLA Plus is you get a different language that's less tedious to write than code, but which gives you the same kind of rigor so that you can check something about your specification before you write the code. So you can do the design in TLA Plus and later you implement. And this works for big systems, also works for small systems. And kind of the icing on the cake of this specification language is that you get verification, okay? Formal verification. Always sounds a bit scary to some people, but fear not. In this particular case, it's pretty easy. And the creator of TLA Plus is this person here. You might not recognize him, so it's actually this person, Leslie Lamport, who made seminal contributions to the theory of computer science, distributed systems, concurrent systems throughout his career. He won the Turing Award in 2013, I believe, and kind of in the later stages of his career, he thought, okay, what would a language, what would a tool look like with which you can design distributed and concurrent systems? And the result was TLA Plus. Okay, so everything he learned about distributed systems, concurrent systems, he kind of condensed into this TLA Plus language. But there is no code, yeah? No code, you can't execute this stuff. Still, it gets used. For example, Amazon engineers at AWS use TLA Plus, and this is kind of the most popular application of it because they wrote about it publicly in CACM, Communications of the ACM. And they used it around 2010 to 2014, and they are still using it when they came up with the initial design of DynamoDB. And the engineers, this replication protocol of DynamoDB, because DynamoDB is this planetary scale database, right? So you have instances of this database in various regions of the world, and then in every region you have multiple replicas for every database, and then you have to synchronize all the data, and the client still wants to get strong consistency, right? That's kind of what DynamoDB does, unless you use it with eventual consistency. And they designed this replication protocol, and then they had whiteboard discussions. Does this work? Does it not work? They had reviews. They even went and built a prototype that they tested excessively with fault-injecting testing and every testing you can think of. Right? In other words, they applied traditional software engineering to the problem. Write a design document, review the design, manually, kind of like a peer review, design discussions, write a prototype, test it, and then ship it. But some of the engineers thought, okay, this kind of the scale that we envision at Amazon, at AWS, since it's so astronomical, we perhaps have to do better. Just to give you a rough idea of the kind of scale they see, I think I read it recently, they handle 90 million queries per second on a flash sale date. Okay, maybe I have one order of magnitude off here or so, but you can see this is really huge, right? And they knew that, okay, even those improbable bugs that never really happen in our test suite, occasionally we have this flaky test that every once in a while pops up, but nobody really knows why it's popping up and nobody cares about. With this massive scale, we are in trouble if we have these flaky things in our system. Because due to probabilities, they just become super likely, right? And then they happen frequently, like daily, hourly or so, and you have people who have to investigate and do live sites and all kinds of stuff, right? So they looked at formal methods, alloy and other formal methods, among which was also TLA+, and they happened to like TLA+ best. So they wrote a TLA+ specification. They kind of learned TLA+, wrote a TLA+ specification for DynamoDB. And this was after everything was after the prototyping stage, right? After everything was tested. They wrote the specification, and then they model checked, ran formal verification on their specification. And this model checker of ours, called TLC, it found a very subtle bug that only takes 35 high-level steps in the global computation. Okay, and they were super surprised because they thought this just works, and apparently it doesn't, or it didn't. I mean, they subsequently fixed it, right? So they applied it to a couple more things, like S3, I believe. You can read the paper on CACM. It's here, Newcomb 2014. I think they give code names to the systems, so they don't officially speak of DynamoDB. But a little bit later, even management was kind of convinced that this is a good idea. And these days, last year, reInvent, Amazon's own conference, director went on stage and gave a shout out to TLA+, among other formal methods. Yeah, they still actively use it. So now you might ask, let's see, oh, it's in a different slide deck, one sec. I have to switch over to this other slide deck, because I want the other, where is it? Oh, dang. Well, I don't have it on the slides, but anyway. So now you might wonder, this was 2014. They wrote a specification for DynamoDB. Since then, DynamoDB has seen 8 years of development, right? People have written tons of new code for DynamoDB. The spec, the TLA+ spec, is probably out of sync. This is a common question people have if I show them TLA+. Okay, we have design documents, but our design documents quickly go scale. Why bother? A, design documents in prose, they are ambiguous, right? You have 2 readers, 3 different opinions. Nobody knows what they mean, and they go out of sync. Well, TLA+ specifications can also go out of sync. People work on the code all the time. But just, and this is missing the slide, just this year, same people published another paper, kind of looking back, and they said, okay, even today, whenever we change anything in the replication protocol of DynamoDB, we go and change the specification and update the specification. And before we touch the replication protocol, we make sure that the specification and model checking the specification confirms that this works. Otherwise, we don't write new code. They still write new code. There are null pointer checks and things like that, right? Small problems, small bugs, easy bugs, shallow bugs, whatever you like to call them. These they constantly handle, right? For those, they don't write TLA plus specifications. But the fundamental design, they get right with TLA plus. Okay, let's see. Oh yeah, so the rest of this event here is just me showing you code and us collectively working on a solution to this reader-writer problem. And you find the tutorial material at this GitHub repository here. So Lemmy blocking queue, Lemmy, that's me, blocking queue. If you go there, you find, okay, there's a README that kind of is written sort of like a book, a small book, like a pamphlet kind of thing. And it starts at the very beginning with just the IDE and the problem statement, and then gradually develops the TLA plus solution to the problem. And also, every Git commit in this repository is kind of one step in the tutorial. So if you want to follow along offline, you can just go to the very first commit and then gradually work your way through the commits and always look at the delta, what's going on. And I have comments written here in the README that explain what's happening. Okay, but let us look at the problem again. So reader-writer, blocking queue, bounded queue. It's pretty simple if you look at the code. We have this Java class here. I believe most people know how to read Java. I also have a C version if you prefer the C version. But C, Java, what do you want? Who wants Java? Okay. Okay, so I have my implementation of this queue here. There's a store, okay, that's an array for some type, depending on what the type the generic here is for the blocking queue. And it has a capacity, a size. And it gets initialized statically, okay? The array here, the store, is statically initialized to some fixed size. Doesn't change throughout the execution of the system. And then there are really only two methods. One is put. That's where a producer adds an element to the buffer, to the store. And there's a take, where a consumer removes an element from the buffer. Okay, and the protocol goes like this. If a producer finds that the buffer is full, well, then it has to wait, right? Fixed size buffer, you can't add anything to a full buffer, so you wait. So we call the primitive, the Java primitive, wait here. Eventually, somebody else will send a notify, right? Causing our current producer to wake up again. So it goes through the while loop again, and this time let's assume it finds that there's room in the buffer now. So it adds the element to the buffer, and it itself sends a notify. Easy, right? I have a few log statements here so that later we can see what's going on. For the consumer, kind of the same story, just the other way around. If the buffer is empty, the consumer has to wait, keeps waiting until it finds there is an element in the buffer, at which point it will remove the head element and previously send out the notify. Okay? There are a few auxiliary methods here in this class file, but they don't matter. Okay, and the problem is, even though this is synchronized and this is synchronized, so they are really mutually exclusive, there's a deadlock here. So who sees the deadlock? Who can explain the deadlock? Yeah?
and it found like it is empty and it is now waiting for it. And then someone else want to put something in there, but that also in the waiting state.
So you said that the consumer finds it is empty. Then it's waiting here, right? So some producer can come in and add an element to the buffer.
Right.
So where's the deadlock? Well, maybe there is no deadlock. Maybe I'm just making a deadlock up. So how do you find out if there's a deadlock? We write a test. We write a test. Let's write a test. I've already written a test, okay? It doesn't use JUnit here in this particular case. It's just an application, okay? So with what configuration, the number of producers, consumers, and what buffer size do you want to test this?
More than one producer and more than one consumer.
Okay, more than one is 3 and 4. Yeah. I think it's, let me quickly check if, I forgot which parameter is what. I have to look this up real quick. So the first one is the capacity, okay. Capacity 3? Bigger? Smaller?
No, it's fine. Just
fine, okay. 4 producers and 3 consumers? Yeah? That's, I think, what I had on the slide, right?
Yeah.
Okay. See our instrumentation here. So it says like, can I stop this? I don't know how to stop this, but you can see it. It says something like C notify, P put, and so on, right? And eventually, I guess, if we wait long enough, we can look at the trace and figure out what the problem is, where the deadlock is coming from, right? Easy. And in the meantime, we just slack off and drink a coffee or something like that. Or leave it running through the weekend. But does anybody else wants to take a shot at this and explain where this deadlock is coming from, why this test runs and reproduces the deadlock? And I promise you there is a deadlock. I'll make this a bit smaller so that you can see the source code.
So a deadlock would typically, for keeping this problem aside, the deadlock would happen when all threads are waiting for the same,
right.
The mutex or mutually exclusive resource. That's just, to theorize it. And now, to integrate into this problem, looks like, all the threads should, just come and, be on the wait.
Right. I mean, again, this is synchronized, right? There is no interleaving between this method here and this here.
Oh yeah. So they'll be waiting to get into this method, right? The method is which holds the mutex. So why would this happen? Yeah, I'm just saying out of depth stuff there.
Anybody else? Well, let's try and see if we can write a TLA plus specification for this problem here, and then use TLA plus verification to analyze it. Okay? So we keep the test running, and maybe we'll be able to reproduce the deadlock before we are done with the specification. Maybe not. Okay, let me go next here. So it created a file, and let me just remove almost everything from this file here, because this is what we're going to write now. Okay, so this is our TLA plus specification. There's a bit of boilerplate here. It's a file, like a class file. It has a header, has a footer. We need a few definitions, few operators like plus and minus and so on, and add and remove. More importantly, we have constances, things that don't change throughout a computation, throughout the execution of our system. So the producers is the set of all producers, okay? If you have 3 producers, producer will have 3 elements. Yeah? Consumers, similarly, is a set. There might be any number of consumers in there. Probably more than 0, right? With 0 consumers, this thing also deadlocks. But this is not the problem we're seeing here. And buffer capacity is the size of the buffer. In our case, I think it was 3, right? And I could have, yeah, go ahead.
Do we require some library for TLA or how?
Libraries. So the naturals and the sequences here and the finite sets is what we call libraries. Okay? Let me just for the moment, oh no, this is not how I meant to write it. I meant to write it this way. C1, C2, C3. Let's remove, that's fine. P1, P2, P3, and buffer capacity is 3. Okay? So our producers are just 3 things. And since we are in a specification language, we don't actually need threads, and we don't have to do a new thread of some kind or some task library. We just need 3 different things that are distinct from one another. And same for consumers. And I think we said we have 4 producers, right? 4 producers. Okay, so the number of these, the sets don't change. So what's going to change are our variables. And I guess we need a buffer of some sort. Okay? And by the way, in TLA Plus, there are no types. It's typeless. I don't know what this is. This is Copilot trying to generate some nonsense here. And I can also make this bigger, I guess. So we need our buffer like the store in the Java implementation. Anything else? Rate of production. You mean like how fast producers add elements to the buffer? So in this particular case, in TLA Plus, you have discrete steps. Okay, you have like a global computer, or where the execution of your individual processes / threads all happen kind of from the global perspective, if that makes sense to you. And since you just do discrete steps, logical time, there is no faster or slower in this world, right? It's just you add something and then you remove it, and how much time elapses in between those 2 states might be hours, might be femtoseconds. That doesn't exist here in this world. So I don't think we need this particular detail. But if you think about the Java solution, there's this notify, there's this wait, there's this synchronize. There's a lot going on behind the scenes, right? The Java runtime handles quite a lot for you. And one thing that it handles for you is managing this wait set here. The set of all waiting threads. All those that are currently, that have called wait previously and that are still waiting. And let me turn off this Copilot here. How do I turn it off? Copilot, open, send feedback, disable. Oh, maybe now it's off. And in Java, we don't see it. And because we don't see it in Java, it's very difficult to see if there's a deadlock, right? Because the definition of a deadlock is really easy. If you have the wait set variable, if the wait set contains all the producers and all the consumers, well, then we have a deadlock. But we can even write this down. Let's call it deadlock. Deadlock. Producers, union, consumers equals wait set. It's set theory that you've seen in high school probably, right? If you have questions, by the way, just ask, right? Just ask. So union combines these two sets, and then we check if this is the result of this is equal to the weight set. And if it's equal, then we have a deadlock, right? Then this formula here evaluates to true. Okay, so what's now just left is for us to define what happens to the variables, the values of the variables, right? So I say initially the variable buffer is empty, okay? Like in the Java code, it's just empty. The syntax might look a bit strange at first, okay? It's a new language, so it has a different syntax. It's something you have to get used to. But what this says really is that the buffer is empty. And these arrows here, they give you a sequence. So a sequence has order and it has duplicates, whereas a set has no order and no duplicates, right? This has order, this has duplicates. So if you add an element here at a certain position, then it will be at that position, right? We don't care what gets added to the buffer, right? Might be images for post-processing, whatever, right? Doesn't matter for our deadlock. Okay, and what happens initially? Oh, this time Copilot got it right. So the initial value of weight set is that it's empty. It's an empty set. These curly braces here denote an empty set. Okay, now you might read this as first this line gets executed and then this line gets executed. And this is what initializes our system. But this is not how TLA Plus works. In TLA Plus, everything is just a formula, a mathematical formula that evaluates to true or false. This one doesn't evaluate to true or false. These is just two individual statements. Okay? So in order to make it evaluate to something and really turn it into a formula, I will put an AND here. Now, in programming, this symbol is typically ampersand, logical AND, right? And in TLA Plus, we like to use this symbol here because this is what mathematicians use. And now it says the buffer equals empty and the weight set equals empty. And if this is the case, that the buffer is empty and that the weight set is empty, then this formula is true. Okay? And if there's something in the buffer, then this formula would be false. But it also gives rise to a state, and we can look at the states in a minute, of our state machine that we are describing. In TLA Plus, we fundamentally describe a state machine. And this is our initial state. Yeah? We start with buffer, empty sequence, and weight set, the empty set. Okay. So what can our producers do? What can our consumers do? Put and take or produce and consume. So let's say a producer can put an element. So this is the producer and some data element, right? This is a definition where we add an element to the queue. So how do you think this would look like? An approximation of the syntax. You don't have to give me the exact syntax. I'm happy to convert it for you. Okay. If buffer, if it's on, yeah, I don't want to use this proposal here. Damn it, really I have to turn this off. This is, used to be possible to just, I have an idea. Extension Copilot. Disable. Okay, hopefully now it works. Okay, if this is empty, okay, apparently I have to restart, right? Okay, let's hope it's dead now. Then, what happens then?
Put something.
Okay, so we have an append operation where we can do buffer the data element. Okay, append comes from this module here, the sequences module.
Actually, instead of buffer equal to empty, it should be like while buffer has a capacity like this.
Yeah, that's a good question. Let's focus on something else first. Okay, in else we do sort of like the wait, right? No, and I think we forgot something here. We also want to notify, right? And we don't have notify, we don't have wait yet. We have to write those two operators in a minute. For now, we don't have them. Okay, but this is not exactly the way how it's written in TLA+, because I said we are going to define a state machine, okay? Init defines the initial state. That's fine. It might define many initial states if you want to. We just happen to have one. This put here, this definition put, is an action or a transition in the state machine. So it takes you from the current state to the successor state. Okay? And in TLA+, we can actually talk about the variable in the successor state. We have a syntax to talk about the variable in the next state, which is like this here. You just put a prime operator on the name of the variable. And now this buffer here in the if is the value of buffer in the current state, or is the variable buffer in the current state, and buffer prime is the variable in the successor state. Okay? And everything inside of this definition here, or operator action, happens atomically, sort of, or like in a transaction. Right? In a state machine, if you go from one state to the next, there is no interleaving with another transition, right? It just doesn't exist as a concept. So we don't have to put a synchronized around this. It just is kind of automatically synchronized.
So one quick question.
Sure.
So buffer size is defined with the less than and the greater than symbol, whereas the wait set sign is defined with
Right.
empty braces, right? So what is the difference? I mean, syntactically speaking.
So this denotes a set, okay, the empty set. This here is just our syntax for a sequence. If we would add an element here, then we would foo bar, okay, and now we would have a sequence that contains two elements, the element foo at position 1 and the element bar at position 2. I could also add foo here again. Now the capacity would be 3, and there would be 2 foos in here and 1 bar. But if we would also try and do the same over here, what's the capacity of this set? 2, right? Because foo...
Kind of a list.
Nah, a list has order, right? And a set... Oh, so the buffer, yeah. The buffer is like a list, or the sequence actually is a list. That's just another term for it, right? And it has order and it has duplicates. A set doesn't have order, doesn't have duplicates. Fortunately, we don't have to define the equals method for our string here and the hash code method like you have to do in Java. And we don't have to choose from a hash set and a linked hash set. Does it exist? I believe so. It's just a set. Yeah? And we could have started with, say, the first consumer being in the wait set. That's fine. That's easy. The first consumer now is blocked initially because it's just a formula, right? We don't have to go and somehow instrument the Java runtime to get our thread to be kind of waiting initially. We can just write anything we want. And this is really the power of TLA+. Yeah?
Why do we use buffer dash in the append? You said it was the future of the
Right, it's the next state of the buffer. So the put here, what happens conceptually in a put operation? The producer checks, is the buffer empty, the current buffer empty, and if it's empty, it adds an element to the buffer. So afterwards, there's one more element in the buffer, right? This is what we've written here, sort of. Okay, so it's really just unprimed variable is the current state, primed variable is the value of the variable in the next state.
But it is still referencing to say the
It's still referencing this variable buffer up here.
Is there a notion of put being executed by one of the producers? Say P1 has to execute put, right? So we are yet to specify that, right?
Right, no, that's missing. This is what this P is supposed to be in the future.
Got it.
But so far we don't have that. But right, we are missing that. We are missing that. Yeah?
Syntax one. On deadlock, you have like a double equal and your buffer is just like an assignment.
Okay. Two equal signs, read it as defined to be or defined as. Okay, in math, in pretty printed TLA plus, two equal signs are this sign, okay? Actually, give me a sec. Export module to PDF. And now you should, oh, I didn't save it. Okay, I have to save it first. Export it again. And now you can see that, see, this is the symbol. This is not equality. This is just defined as. We just give a name to a formula. And then you can use the name instead of the formula. It's just for the reader. It reads nicer that, oh, this put kind of communicates something, right? But it's just defining the formula if, yada, 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 to have the name put and to require these two parameters. The equals here, this is really equality. Okay, this really is true if buffer is equal to the empty set. Unfortunately, in TLA plus, there is no assignment. So I don't have to show you assignment. Because this kind of here, and the way it really has to be written is actually this. Kind of implicitly assigns the next value of buffer, but it's still just equality. Okay? So
Even the above one, where you say init equal the buffer, that's not assignment.
this one up here,
Yeah, where you buffer comes in, right? Like
line
line
number
number
14.
14 or 15?
14, 15. Buffer
15.
equals,
This is also just equality. But in our statement, so what this formula, so assume a universe of buffer and with the two variables buffer and weight set, and they can really have any value, these two variables, any value whatsoever. They could be 42, the value of buffer, or a Shakespeare drama. But you only care about the variables when they have these values. Okay, so kind of select from this universe of all states with these two variables those for which this formula is true. Okay, and the tool then obviously works differently, but I'm not going to talk about the tool here because that's just confusing. Okay, the mental model is we don't have to care how we construct these states. We kind of just say, define that these are the states we care about. Okay, and this is why we just use equality here and don't use assignment. We don't have to construct these states. This is done for us magically. We just select them here. So we select out of all possible states the state where buffer is equal to foo bar foo and weight set is C1. Okay? And out of all the states, we select 2 with this formula, where the current state is buffer is empty. Don't say anything about the weight set. Don't care about the weight set. And in the next state, the buffer has this one extra element. Yeah. Okay. And so we find a state where this, we find 2 states that are connected through a transition where this is true. But once we have a bit more written here, I can generate the state graph, and then we can look at this graph, and then perhaps becomes more clear. Okay, so we have to get rid of these squiggly lines here. So let's quickly define notify. Nah, notify, and let's define wait. Okay, who wants to take a shot at notify? So syntactically, this should be mostly correct now, but what should we really put into notify in the definition of notify or wait?
Take something from the weight set.
We take something from the weight set, right? Notify essentially just removes one element from the weight set. We don't care which one. It's a set, there's no order. We can't pick the first one. We just pick one. And in the weight, well, we add this p to the weight set. So weight set union p, okay? And this is the value of weight set prime in the next state, all right? So we have a transition where we add this one element to the weight set. Okay, so to remove an element from a set non-deterministically, I have to do it like this. In weight set, oh no, it's lowercase, such that weight set prime minus this n. And let's use the, let's use here p. Let's use p. So this formula says there exists a p in the weight set such that we can remove it.
So in the weight, when you use line number 2.
Oh, hold it. There's another weight set here. Okay. Say that.
So in line number 21, you use union, weight set union. Why do we have any like append or like append?
Well, append wouldn't make sense because append is kind of like at the end, right?
At the end.
And there is no end in the set.
Right.
You can only like just throw it in there, and you don't know where it ends up. So that's why it's called union here.
Just one bit since you know that. So put is defined as P and D, right? So P is essentially something which would have just been DQ'd or removed from the weight set, and it's ready to. So how is that P magically?
Oh, there is no magic. We're just missing the definition. We still have to do the definition. Just
Sure.
okay. So there's one problem here. So this could be empty, right? This weight set could be empty, and in this case we cannot remove an element from the weight set. So I'm going to put the weight set equals the empty set. Well, then weight set prime equals weight set, else this other thing happens. Okay, so in the case that the weight set is currently empty, then what this is saying that in the next state it will still be empty. Okay, and I'm not going to try and remove a non-existing element from a set. Yeah, I guess in Java you would get something like a no such element exception, something like that. Okay, and I guess we could also move the else here that perhaps reads a bit better. But try and contrast our notify and wait with what is probably the implementation of wait and notify in the JDK, in the JRE, right? I mean, I once looked at pthread in glibc, pthread broadcast, that's notify all, signal that's notify, and I think wait is in pthread is called just wait, and I think it translates into 800 lines of C code, right? Because you have to guard these data structures. There are races potentially, and you want it to be super fast. All these kind of concerns you care about in programming. Here we don't care about this. Here we just abstractly want to define what's actually happening in the algorithm. Yeah?
I was just thinking one way to think about it is basically you're looking at states, right? Like, I mean, whatever we have there represents the states, and then you've taken out everything else, and then the transitions. And I think maybe to think of it from an execution perspective, right? The prime thing basically says this is the other state that we care about.
Right.
And that's it. These are the states. And
right.
Yeah. So that kind of eliminates a lot of the coding.
Right. That's the main idea. Eliminate most of the coding and really only focus on what's important.
On the states. I mean, in this case, it's
Yeah.
the states.
Right. Okay. I think there is also like a get. That's the consumer here, I guess, that carries out the get. And this is like if buffer is, okay, so this is actually upside down, right? This should have been if the buffer is not full. So if the length of the buffer is not equal to buffer capacity, right? Then we can append. Otherwise, we could have only appended if the buffer is empty, but we want to be able to append if the buffer is not full. Okay, so now if the buffer is empty, in the consumer case, it makes more sense to check the empty buffer. Well, then wait, right? The current consumer. Else, buffer prime equals the tail of the buffer. There's a tail operator here that we are going to use that essentially just strips off the first element. Do we need the first element? The thing that comes out of the buffer?
No.
Don't care what it is, right? And notify, right? Notify. Oh, that is capital. No surprises so far, right? More? Other questions? Feel free to ask questions at any time.
So I'm just speculating, all right? It might be getting ahead of what it is. So does TLA plus, eventually you'll be executing this, right? And it would generate perhaps a state, a machine of sorts. And if there's a deadlock, then it wouldn't be a directed acyclic graph. Maybe there'll be like some cycle.
Yeah,
of states.
sort of like that. I mean, it's the right intuition.
Yeah, that's an
Okay, let's first find these P and Ds that we've been on and Cs that we've been using. Because now we kind of tie it together, the put and the get. So I guess a get can happen with some consumer, or, and this upside down A is an or. It's like this in programming, but we just write this symbol here. Whoop. Symbol here. Or a put can happen. Put P and some data value. Okay, but we still don't have C's and P's. Where do we get those from? From the constants, right? So there exists a P in producers, such that, let me just rewrite this, move this down here. Okay. And similarly, we write there exists a C in consumers, such that get. But that's not really it, right? What's wrong with this one? Okay, that's another question. Let's first, I'm happy to answer it. Just let's first think about what this really now does. I couldn't hear that. It's a bit noisy here. There are also idle states, right? They happen automatically here. But I can show you where they're coming from if you want to. But no, in terms of our termination attack, of our blocking queue here, there is something fundamentally wrong. So there are obviously threads that are on the wait set right now, right? And can those do a put, or can those do a get? No, right? They can't execute. So I guess we remove the wait set here. Okay, otherwise we would have kind of executed threads that are blocked. That would probably cause problems. I guess there won't be a deadlock anymore, but I'm pretty sure that our data structure would be corrupted. So then the question, why are there ORs?
No, I think I got the answer to that. Like, it could be any of these.
And essentially we are in the current state and buffers, let's say we are in the initial state right now. Buffer is empty, and the wait set is empty. And now it's possible for a consumer to try and get an element from the buffer, or for a producer to produce an element, or for any other producer to produce an element. So you have multiple outgoing transitions from the current state. And unless we screwed up, let's go back to this being empty. Keep it simple. I think we should be able to execute this now. Blocking QCFG. Let me just quickly, we already have a CFG file. That's perfect. Let me just find it. Okay, so we won't need these constances here. Blocking QCFG, init and next. This is just configuration for our model checker. I won't talk much about it. This is just a piece of syntax that says the init formula is called init and the next formula is called next. By the way, this hasn't deadlocked yet. Okay, our test is still running. And this can actually deadlock. It's just probabilities. Okay, so let's see if we can check the specification. Check model with TLC and dump.bq. Okay, I forgot a few things here in the heat of the moment. Model checker says I didn't give values to all the variables. And I always have to give values to all the variables. So here's a state where the buffer is undefined. Okay, let's quickly do that. So, and unchanged or buffer prime equals buffer. And the same, I guess, we need this particular case. If a producer or consumer has to wait, then nothing happens to the buffer.
Can you explain this again? Why did you have to do this last?
You mean like this one here?
Yeah, the assignment.
So we always give values to all variables. That's like a fundamental law of TLA+. You always give values to all the variables.
Every step needs some assignment to everything.
There is no assignment, but there has to be a definition that says what the value is.
And also, I noticed since there's a concept of a scope here, like it's like global, right? Like buffer can be assigned in whatever you call.
There are only global variables in TLA+. All the variables are global, and
So it could happen across these invocations that everything gets assigned.
yeah, right. Because the reasoning is easier if you only have global variables. That makes reasoning easier, and that's the reason why all variables in TLA+ are global. There are no scopes, there are no local variables, everything is global. If you design a distributed system with TLA+, it's possible that you shoot yourself in the foot because you read the value of a variable from a remote node. That can happen. You have to be a bit careful. But specifications are short enough that you typically find these problems before you implement the system.
And
So,
convention is that prime thing which helps you match. That's pretty much it.
right, and the prime is there to talk about the next state. Okay, let's see if we now. Okay. Ooh, it's a bit too big, I think, because it already has almost 500 states. I'm pretty sure that should we render the state graph, it will A, take forever to lay out, or go out of memory. I mean, we can try, but there's probably not much to see. BQ here. Yeah, see, it's rendering right now. And let's give it 10 seconds, and if it doesn't come back, we kill this one and open a different one.
Is it deadlock or is it still running?
So this is kind of like graph viz running in the background now, trying to lay out the graph, like where to put the nodes and where to draw the transitions. And I think that's NP complete, right? The problem.
Still running, is it? It's still checking? Or?
Oh, you mean our test case?
Yeah.
Our test case is still running. No, I'm just talking about the render for the state graph we're going to see, which has nothing to do with TLA+. Nothing to do with TLA+. But this one is stuck. So what we can do is, let's just make this fewer elements, and then we should have fewer states. And then it should be easier to render the state graph. Check model with TLC, dump. OK, now we have just 4 states, so I guess our rendering algorithm has a chance of finishing in finite time. And yep, this time worked instantaneously. So now, okay. Now we can see what our state machine or the state graph for our specification looks like. Buffers, this is gray. You might not see this, but this is actually gray. That's the only gray state because it's the initial state. Buffer is empty, wait set is empty. Yeah? Empty sequence, empty set. Then there's a transition here that takes us here. So the consumer C1 is in the wait set. That's apparently a consumer that tries to remove an element from the buffer. It does the get operation. This one here is a put operation, clearly. From here, we can go back to here. That's then the get operation from this state. Or if another producer tries to produce again, it goes to the wait set. Okay, so this is produce, and the second time it goes to the wait set. From here, we can go back to here by consuming an element, which implicitly, or as a side effect, removes the P1 from the wait set. Do you see a deadlock? There is no deadlock here, right? Wait set is never the union of producers and consumers. So maybe I lied. So maybe there is no deadlock here. Maybe this will never deadlock. Let's see. So let's go back here again. Let's add a second producer.
How does it know when to stop?
Oh, how does it know? The tool knows how to stop. So that's again a question about how the tool works. It just does, it enumerates all the states, kind of on the fly generates the state graph and runs breadth first search on it. So it keeps a data structure, a set of known states, and when it gets to a point that it cannot generate unseen states that are not in this seen set, then it stops.
Some kind of cycle detection, some rough.
That is automatically kind of cycle detection. You go through a graph, if you do breadth first search over a graph, and you have in breadth first search, you have a queue of unexplored states, and you have a set of known states, of seen states. At some point, your queue will be empty, unless you have an infinite graph. Then you will keep going forever.
And in this case, why did it stop? Like here, what happened?
Because there are only 4 states. There are no other states. The buffer size has capacity 1. And there are two processes. There's one consumer, one producer.
Even in the previous case, it was able to enumerate all the states. It's just that the visualization.
It was just the visualization that got stuck. Okay, perhaps I shouldn't have mentioned it. That was perhaps more confusing than 3, 4 producers and 3 consumers. That had like almost 500 states. So these visualizations are neat if you do small problems, but for real-world problems, they're pretty useless. Because specifications have millions of states, and then you can't see anything. I think there's a question.
Very basic question, but are we modeling concurrency here?
Oh yeah, absolutely, right? I mean, to be precise, there is not much concurrency in our original problem description, because put and take are both synchronized, so they are mutually exclusive, right? So there is no interleaving of a put and get operation. But still, it might be that put happens before get, or that get happens before put, and we have all these possibilities, right? We can just traverse this graph following these lines and create paths from this graph that give us all possible executions of the system, right? So you have the concurrency in there. Okay, so we have P2. So I added one more element, one more producer to the system. Check model with TLC. Let's do it again. Okay, now we have 14 states. That should still be possible to generate. PQ, okay. Reorganize the windows here. And it's perhaps a bit too small. It's a bit sensitive to this zoom here. But okay, we start up here with the initial state, okay? We traverse through the system. Here P2, here you see P1. I guess both of them individually try to add an element when the buffer is full. Both are now in the weight set. Let's make this a bit smaller. You need a mouse wheel.
That is fine. Whatever you just showed is fine.
Okay, this is fine. So we can look at all these states, and down here, there is our state where we have the deadlock, right? Here, all of our threads are in the deadlock, are in the weight set. And sure.
See the previous states. Yeah.
Okay. So there's a deadlock for 2 producers, 1 consumer, and capacity 1. There is no deadlock for 1 producer, 1 consumer, and capacity 1. And I think our test case runs with 3 buffer capacity, 4 producers, 3 consumers. So let's see if I fooled you, and this thing will actually never find a deadlock, because there is no deadlock with this configuration, or if there's a deadlock with this particular configuration. Let's go back here. Okay, and buffer capacity 3. But if we now would try to generate this graph, it doesn't work because it gets too big, right? Instead, what I'm going to do, and it's a bit tedious to look at these graphs and look for a state where you find the deadlock anyway, right? And you don't want to do this. So let's use our definition down here, this deadlock definition. But let's just negate it, okay? Instead of saying this is a deadlock, this is the definition now of no deadlock, okay? And we want the tool to find the state where this gets violated, where this is false, okay? That's why I have to negate it real quick. And now if I go to our config file and check this as an invariant, okay? What is an invariant? Well, that is always true, right? It's always true. It's always true. In every possible state of the system, deadlock ought to be true. Well, probably it's not, because we know our system deadlocks, right? Okay, so let's close this one. Check model with TLC. We don't need this graph anymore. And surprise, there is a deadlock, even with our buffer 3, 4 producers, 3 consumers. It just so happens that this shortest counterexample, the shortest sequence of steps for the system to deadlock requires 47 high-level actions, high-level steps in our system, for a particular sequence of 47 operations for the system to deadlock. And our unit test is just a bit unlucky. It generates the wrong sequence of states. And now we could try with testing, we could try to create artificial load on the system so that it explores different schedules. But it's all just probabilistically, right? There's no guarantee that you will ever find the deadlock with testing. And even if this deadlocks now, okay, you would have to study this trace here and where is it? It would be very difficult to figure out what the problem is, right? And you might find, oh, I forgot to add a log statement, and now I have to rerun this whole shebang again, and I have to yet again wait a few hours. Here, our model checker, it's, at least in this particular case, super fast. Sometimes it also takes a couple of hours for real-world specifications, but it's deterministic, okay? I can click on this any number of times. In the same amount of time, it will always find the same counterexample. Okay, we still don't know what the problem with the deadlock is, right? And I'm not going to explain it to you with 47 steps, because that's a bit too complicated. I probably would mess up. But let's go back to our previous configuration. That we know deadlocked. So this one has, check again, 9 steps, okay? Maximum number of steps is just, for this, not the maximum, the minimum number of steps for this to deadlock is 9 steps. So it shows, and that's the nice part, this trace gives you the value of both variables for every state of the system, from the beginning of the execution to when it deadlocked. Not just the state in the terminal state, but all states.
All the variables here would be shown.
Right, you see all the variables here and their values in every state. Okay?
Can you make out the transition, like which ran, what of these things ran?
So you mean like the names here?
As in, like,
If it's a put or a get?
one to state 2, but which line in the thing made it go to that?
Yeah, we can see that too. I can rewrite this slightly. If I would rewrite this a bit, then we would also see put and get here instead of just next. Okay? But due to the way it's currently written, because I did it on the big screen, it just puts next here. You have to be a bit careful so that it puts names here. But I could just, if it helps, we could just add an action variable here, and then every time you do a put, you set action to put, and every time you do a get, you set action to get, and then you would have the logging. But typically, you don't need this. Okay. So if you use TLA Plus productively, you would probably now spend an hour or so looking at the traits. Okay, even though this is just 9 steps, this is already pretty complicated. Because computer science problems are complicated, not because TLA Plus is so complicated.
Can you get a sense of how it explodes here, in a sense like from one state, what is the number of next states potentially?
So the number of next states, you could go back to the state graph, and then from there see what the number of next states are.
Can you get a sense at
we have a debugger, and the debugger shows you what this number, what the set of successor states is. If you are in the current state, I don't want to show you the debugger right now. I'm happy to do this offline, but it requires me clicking for 5 minutes, and that's boring. Okay, so typically you study this trace. You have to think through it, argue through it, reason through it. If you have the time, you can even animate it. So here's the animation for 4 producers, 3 consumers, and buffer size 3, 46 steps, frames, or 47 actually, and it's animated. It's a bit too fast to understand. But I also have it for 3 processes. Okay, so this is the first frame, first state. Everything is just initialized. And P2 is in the next state going to add this element n into the buffer. Where's the next button here? I guess I just have this. Okay. So in the next state, as I said, n is now in the buffer. P2 is still the currently active thread or process, and it tries to add the next element into the buffer, and it can't, because now the buffer is full. Okay. Oh no, I think we went back now. Nothing is happening. So, because the buffer is full, and P2 tried to add an element to the buffer, P2 gets blocked. It's now in the wait set, right? It's part of the wait set now. Schedule means that this is the thread that executes next. So that's the scheduled thread. Okay, you can also ignore it, but it's just a piece of extra information here. We don't have it in our spec. For this, I wrote a slightly different spec with a bit more information. So the system scheduler, the Java runtime, decided, okay, now it's P1's turn. Okay, that's why it gets scheduled, and it gets a chance to add a buffer to an element to the buffer. But it obviously can't because the buffer is full, so P1 gets also blocked. Now they are both in the wait set. No problem, we have C1, right? And C1 can now save the day and consume the n from the buffer. That's happening here. And it notified P2. Okay, P2 is no longer in the wait set. It can be scheduled. It's part of the runnable threads, but it's not scheduled, right? But it could, in theory, it could execute. It's no longer in the wait set. Okay, C1 now blocks because it tries to remove another element. We kind of have an eager scheduler here, right? It gives control to, or whoever has control can keep control for as long as they can execute. But yeah, typically we don't know what the regime of the scheduler is. Okay, so now P1 can add another element. It's going to add h to the buffer, and it itself, after it added h to the buffer, it notified P1. Okay, P1 is now enabled again. And P2 tries to add a thing again to the buffer, gets blocked. P1 tries to add an element to the buffer, and now they're all blocked. So there's a deadlock. Even though the code, this Java code is fully synchronized, there's no interleaving here whatsoever between take and append. There are no data races here. It has nothing to do with the Java memory model. There is a deadlock here. It's an algorithmic deadlock. Yeah.
Can we use notify all instead of?
That's a good idea. So the problem is here, right? Between those two frames, you can see that P2 should have notified C1, right? But it notified P1. So it notified the wrong thread. Notify all always notifies all the threads. So what would be the definition of notify all?
If the wait set contains something that is form of.
Even simpler. Wait set prime equals the empty set. None of the threads are waiting anymore. That's pretty easy. Again, in the implementation, P thread broadcast in glibc, several hundred lines of code, right? Because they are efficient about removing all elements from a set. Okay, now let's change this. Where is notify all and notify all? And let's see, check model with TLC, and yep, this works.
So one question here. So when we in the state diagram, we try to explore like a deadlock.
Yeah.
So by going through each of the frame, then only we have to identify, like, okay, this is the problem. And then,
Say that again.
so like when we are showing the three
Are you-
nine state diagram,
Okay.
PowerPoint presentation.
Oh, the PowerPoint, you mean this one here?
This one, yeah. So like when you identify, okay, why this deadlock is happening, okay. So you identify, okay, 7 or 8 frame, okay, this frame having some problem, and then you analyze, okay, because it is not notified all, then only you trigger this, or how do you come up with a conclusion?
I mean, typically you look at this trace here. Okay, this trace is the textual representation of this animation. I was just a busy beaver and I created this more or less beautiful looking animation. You can do this with TLA Plus. It just requires a bit of more extra work, and typically it's not worth it because you only look at this trace once. So what I'm saying is you don't get this animation for free. You can do it, but most of the time you just look at the trace. Okay, but the information is in the trace. All the information you need is in the trace. Actually, this is all the information that exists about the system. So you have all the information, all the data available to you. You don't have to go and scrape log files from some system, especially if you're in a distributed systems world and you have multiple nodes. You don't have to go and log into that machine, download 2 gigabytes of log files from there, merge it with the other 2 gigabytes of log files over here, and kind of match the timestamps, and now you find, oh, the clocks are not synchronized. Dang. So this is all here inside of the specification. I think there was a question in the back. You have a question? No? Okay. Okay, so notify all, I just reverted it back to notify, but notify all works. Check model with TLC. Everything is fine, success, green. That's nice.
I have several comments here. One that if you see line number 39, it almost looks like math, that there belongs C in a set of consumers. Right?
I wouldn't say almost. It looks like math because it is math. If you pretty print it, it looks even like real math.
Oh, yeah.
Intentionally, Lamport, when he designed TLA Plus, was like, okay, what kind of syntax could I use? I could use some programming language syntax that was invented 10 years ago, or I use math that was invented 2,000 years ago and pretty much everybody is familiar with, except programmers.
And the second question is, in the Java code, we actually specify that this thread has to be consumer, or this thread has to be producer, but in the TLMS we have not specified like that this thread has to be specifically consumer. So
Oh, yes, we do, because it's this formula here that says a consumer can only do a get operation, and a producer can only do a put operation. So this mapping here from consumer to get and producer to put happens here.
Is that like the, on the notify all thing,
Yeah.
the change, is that like a common solution to a lot of these things? It seems like a nice hack.
That's a good question. I mean, it works. It works. But if you think about it, so here our notify all really looks elegant and clean. But if you think in terms of the implementation, and if you look into pthread, glibc, blah, 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 then you will find that to do a notify all, you do number of elements in wait set notifies, right? So you do a for loop for every thread in the system. Now imagine you have 1024 threads in the system. You have to notify 1024 threads. So the solution works, but I would argue it's perhaps not the most elegant one. Yeah? It's like sledgehammer approach here. Works, but you would now have to go and measure what the performance of this is. I tried to actually come up with performance measurements for notify all, and another solution we're going to see soon, but it was very difficult. It even seemed as if notify all is faster, but I was only testing it on a machine with 16 cores, I believe, so maybe I wasn't seeing the effects. But you have cache lines and all these system-level concepts, right, that interfere with your measurements, that it's very difficult to get these numbers out. But conceptually, I think you all agree with me that notify all seems like more expensive, right? So what could be the alternative to notify all? Notify doesn't work and notify all doesn't work. Those are the only two methods we have in Java, but here we are not constrained by an API somebody else came up with, right? We can do whatever we like. So what could be the alternative?
Notify is just a class of thread.
Right, notify other.
Other, yeah.
I call it notify other. So that looks probably like our notify, but we have other. Let's say the others are represented by O. And let's say if wait set minus, do we minus other? Now I have to think which way around I'm going to implement this. So here, if we can put consumers in here, and here notify other, we add the producer, so producers and consumers. So we remove, no, actually it's easier if we do it this way around. Producers, consumers. So if wait set minus O equals empty, then wait set prime equals wait set. Else there exists a thread in wait set minus the others, such that wait set prime equals wait set minus t. Right? I think this should be it, right? So the producer, when it notifies the others, it passes all the producers. So we remove the producers from the wait set, and therefore there should only be consumers left in the wait set. If what remains is empty, well, then there are no consumers to be notified. Otherwise, we choose one of these, we pick one of these threads from the wait set that are consumers. And vice versa for the other one.
So could you explain that again, whatever you just wrote?
This one here?
Yeah, the 2 lines.
So the only difference between notify and notify other is that we have this set of others is a stupid. Us. Let's call this us maybe, because this is really our type, right? Sorry, terrible name. I can't come up with a better name right now. But a producer, should it notify the other type, the consumers, it passes all of its kind, so to speak, into the notify other method. This is us now, okay? And then we remove all of us from the wait set. And if what remains is empty, then nothing can be done. Otherwise, out of those that remain, which are now only consumers, we pick one non-deterministically and remove it from the wait set.
Producers notify other producers.
No, consumers. The important point is that you notify, that a producer notifies a consumer and that the consumer notifies a producer. Because if you go here, it's frame number, where was it? In this frame number 6 here. The P2 is the only one alive, so to speak, and it notifies a producer, and this is what gets us into trouble. It should have notified the consumer. Okay, so.
This is weight set minus, so it's a set difference weight.
Right, this is set minus, exactly. This is set minus, just removes the right-hand side from the left-hand side. Check model with TLC, and now the question is, does this work? Notify all works. What do you think? Does this work?
I have a question. Okay, the put method, right? Like is the one which is notifying producers.
No, yeah, it reads a little bit, yeah, my naming here isn't, but really it's, yeah. Should probably notify not these guys here, okay? But for now, I will just keep notify others. Okay, and this apparently also works. Unsurprisingly, the sledgehammer works, the scalpel also works. Okay, great, awesome. I think we found the source of our deadlock. Now the question is, how do you implement this notify other? That's one question. Well, I will leave as an exercise for the reader. But the question is, let's see, do we have the slides here? Yeah, is everybody happy now? Assuming it would be Friday, would you feel confident to ship this now to production? Deadlock is gone, right? But do you think our algorithm here, the one that we implemented, really works? Assuming we implemented whatever we specified. Nothing happens. Yeah, that's a different problem. It's also related to liveness, but that's not what I mean. Should I finish or? No? Okay. There's another problem here, because all could just stop and not do anything. Typically, that doesn't happen in systems, that they just all stop unless somebody pulls the plug and the machine is off. But in all other cases, the runtime typically schedules threads all the time, right? But there's another problem here with our solution. What kind of guarantee we might want to add to the system? Say that it's satisfied. Shutdown. Shutdown is an interesting problem. Blocking queue shutdown is interesting. I have 2 solutions to that problem in the GitHub repository, but they are the final exercises. So that's more sophisticated. You need something like a poison apple, poison pill approach. And surprisingly enough, if you go on to Stack Overflow and look for this, most of the answers are incorrect. They only work for particular configurations where you have certain ratio between number of producers and consumers. But for the universal, the generic solution, I think I've only found it in what's the name of the book? Java Concurrency in Practice, something like that. So they have the correct solution. And they use this poison apple approach. No, but that's not it. We could add it here, but this would be an additional concern. But there's something else problematic with this solution. So suppose we use our queue here to build some kind of business process, and every front-end producer represents a customer. And some consumer post-processes something that the consumer that the producer, the customer kind of requested. Okay? Do you think that all of our customers will be happy?
With a timeout and time.
No, there's no timeout.
All of the consumers can pick the same customer.
No, that's also not the problem.
Priority.
Yeah, priority goes in the right direction. I think in computer science, the term I'm after is starvation. Okay? We want to make sure that all the customers are serviced. Right now, we don't have a deadlock. But that doesn't mean that it's impossible, or that doesn't guarantee that all the producers will eventually produce. It only means that some producer will always produce. Might always be the same producer, right? Might always be thread number 1 or thread number 0, and all the other threads still get stuck. And then you only have one happy customer, and everybody else is kind of annoyed and moves to a different company. Okay, unfortunately, in TLA+, it has first-class support to specify this so-called liveness property. So far, we specified a safety property, something bad must never happen. Now we specify the good thing that eventually happens. And the good thing here that eventually happens is that for all producers and producers,
All of them in wait set, they eventually.
yeah, don't necessarily have to be in wait set, right? Because a producer could just produce and then be done, and it doesn't get added to the wait set. So what we really want is that every producer kind of eventually does a put operation, okay? By the way, let me just do a minor modification here. So this is essentially what we might want to say. I have to add a little bit more here. Conceptually, I want to say all the producers eventually produce. And they do this over and over and over again. And this eventually over and over and over again, I can specify with temporal logic. And this is where the T in TLA plus comes from, temporal logic of actions. This might now look unfamiliar to you, but what I'm saying here is that always, that's this box thing here, the box symbol, eventually, that's the diamond, always eventually this put operation happens. Another way of reading this is repeatedly. Repeatedly, we do a put operation. And for reasons that we should not care about today, I have to add wait set buffer here, but ignore this last part, okay? So, where's our config file? Guess we don't need this here. Config file, property starvation. And, yeah, okay, I have to do a bit more here, but just bear with me because I'm not going to explain this. Just give me a sec. We need this here and have to replace this with that. And now if we check this specification, we should find, okay, yeah, there is a violation here. If you have more than one producer, it's possible that we end up with this cycle here. Yeah? Exactly the cycle that I mentioned, where I guess P2 is the only producer that ever produces, and P1 never gets a chance to produce. Doesn't deadlock, but it's unfair. And because TLA Plus has this first-class support to state these fairness properties or liveness properties and can check these liveness properties, we also can find liveness hashes in our system. And we can also say what has to happen for the system to satisfy liveness properties, which is this part here, but I'm not going to explain it today. But, oh, I think the test has finally deadlocked. No. Let's see. Oh, I killed it? Ah, okay, I killed it.
Coming back to that put PP that you just added over there, right? Like, change it from the
Which part are you talking about? Which line? 49?
yeah, such that put happens. Where was that?
Oh, this P here instead of data.
Here, oh, right over there. Yeah, the one that we just pointed out.
This one here, 44?
Eventually, it will always happen that part. Right?
This part
Yeah.
here.
So what it does it like? Is it like it checks that this method is called with this parameter?
Yeah, kind of.
At least not.
So yeah, that's how the model checker checks this. It looks for the. That could be a talk on its own, okay? In a nutshell, it searches all the cycles in the state graph, actually in the behavior graph, for cycles that don't satisfy this formula here, okay? Where there's a cycle where this is never true. Yeah? 15? Yeah, I think I'm mostly done here. Just want to wrap up. So the short answer to this particular problem is obviously not that you specify a solved problem with TLA plus, because if you go to the array blocking queue in Java, it exactly implements this solution in a slightly different way. So it has a lock instead of our solution where we use the instance mutex, the synchronized keyword. Here it has a dedicated reentrant lock. Okay? And the reentrant lock, from there we derive two conditions. Two conditions, not just one condition. Two conditions. The not empty condition and the not full condition. And the producer, I don't know if the producer notifies the not full condition or the not empty. What's important is that the other type, the consumers, notify the other condition, right? So they kind of use different conditions. And that's why it works in the array blocking queue. Okay, so this problem has been solved in the array blocking queue of Java by using this reentrant lock with two conditions, very important. And then somewhere in here, I don't remember where, maybe in the, here in the constructor, you can see it passes fair into the constructor. And if fair is true, then we get a reentrant lock that guarantees that there's also no starvation. If you initialize the array blocking queue as unfair, then you're okay if certain threads, certain consumers, producers starve. Don't know what the default is. The default is unfair. Okay? And I've at least, I think, in Elasticsearch seen a problem where they had this unfairness problem, the starvation problem in practice. It wasn't kind of bigger context, but anyway. So TLA plus, to wrap up, you can define the state machine pretty elegantly, I think. You can define the state machine here with init and next, and these in between get and put. You can define safety properties, something bad that must never happen, or the bad thing that must never happen, and liveness properties, the good thing that's eventually supposed to happen. So if you want to follow up now on this one, I think we went through 1, 2, 3, 4, 5, 6, 7, a couple of these steps in my tutorial, offline tutorial. Oh, by the way, just so you know, this relation with the deadlock is if the buffer is 2 times, where is it? Where is it? I have the formula somewhere. If 2 times buffer capacity is bigger than or equal to the cardinality of the sum of producers and consumers, then there is no deadlock.
Awesome. So I believe such a correlation will purely be possible only because we have TLA plus, right? Because we can quickly experiment with this kind of combination.
Right. I mean, you could also kind of wait for all of them to deadlock and then plot this chart.
Like
but this would be, yeah. I mean, I only could go as far as, I believe, 8 total processes in the system and a buffer of capacity 3. At that point, model checking took too long. There's obviously exponential state space explosion happening if you do model checking. But it was enough for me to infer here this chart. So yeah, I think we are currently at step number 13, and then a few more. In between, I also show that you can write a proof in TLA. If you want to prove something correct for any number of producers, any number of consumers, every buffer size, buffer capacity, you can write a proof. And then it's mechanically verified. This is kind of like the gold standard in formal verification. That's possible with TLA+. I show how it's done in this tutorial. It's a bit advanced. Typically, in engineering and programming, we don't write proofs. I also have this nice part here where I now check if my high-level specification and the implementation conform with each other. So that's a trick you can do to make sure that the implementation actually satisfies the specification. But it's just probabilistically checking it. It's not, there are no proofs or anything. It's not model checking it. And yeah, later steps, I think, also talk about the termination. And I do refinement and all kinds of other things of TLA+. So you could follow up offline if you want to. Okay, other questions? Yep.
So, when translating spec into a programming language, right? How do you kind of guarantee that? Because when you're converting that, it's possible that, for example, here when you're looking, the simplest assumption is run to completion, right? Like if you take a one single step, it's run to completion. But that might not translate as well when you're converting to a function.
Right. So I personally use TLA+ in kind of two domains, 2 problem spaces. One is distributed systems. If you describe a distributed system with TLA+, you typically describe, if you translate the spec into code, you translate 1,000 lines of TLA+ into 100,000 of lines of code. There is no chance for you to formally prove that one implements the other. That's not the point of TLA+. You want to make sure that whatever you implement, that you stand a chance to implement something that actually works. If you apply all programming tricks to make sure that your programming is proper. So in other words, make use of every technique, let it be formal methods or testing or property-based testing, to make sure that your actual programming work works or the programming is correct. But you could still implement a broken algorithm, right? And TLA+ helps you to not implement a broken algorithm. If you design TIMSort2, the next better sorting algorithm, and you spend 2 months on the implementation, but then you find out there is a certain input where this doesn't sort the input sequence, or you have wasted all these weeks on implementing something that's fundamentally broken. Then you can try and patch your implementation, and this is typically how we work, right? We keep adding patches and patches and patches to the implementation until the point that the whole system collapses under its own weight. Because nobody can maintain this anymore. You have all these corner cases, left and right, that you have to address. And TLA+ wants to help you to reduce the number of corner cases up front. If you do more low-level concurrency specifications, there you typically use a dialect called Pascal, which in the case of the, let me show you real quick. So where is it? Pascal, it's a Pascal branch here. So this is the same problem specified in Pascal instead of TLA+. And here you can see, okay, we have syntax to do processes. You have if, then else, you have while loops. It looks a lot more than imperative, like an imperative programming. And translating this into code is kind of copy-paste snippets into the code in a comment, and then you just manually translate it. This is how I do it.
So could you recommend the first step as to TLA+?
Absolutely. You should always start with a TLA+. Once you're done with the TLA+, you start working on your implementation. It's kind of like prototyping, except that writing the prototype becomes a bit cheaper because the specification is, the language is super expressive. You can check safety and liveness properties. And also, like in this example, we can make this weight set explicit, right? In code, this is completely hidden from us. You can't access what's going on in JRE. It's opaque, right? Here, everything, because it's just math, everything is explicit. And you can abstract these concepts into what you care about. Like I said, 800 lines of code to do this broadcast, this notify all. Here, it's just a one-liner because we don't care about all this detail.
I just want to take a short pause here. So we have time till 1 o'clock, right, for the session. So maybe if it's okay, we can take a break right now.
Yeah, no, I'm done. I'm done.
And then maybe we can come back.
The official part is over from my perspective. So I'm happy and stay here and answer more questions. No problem. Oh, good question. Where can we learn more about it? So Les Lamport was nice enough to record a TLA Plus video course that you can find on the web, aka.ms/TLA. Just look for TLA Plus video course. Will be the first hit on Google or Bing, where he, over the course of 11 episodes, well, it's like 12 episodes, explains TLA Plus, front to end. Starts from the very basics and arrives at liveness and fairness and so on. While studying various different problems. Die Hard, that's from the movie. You have 2 jugs and 3-gallon jug, 4-gallon jug, 5-gallon jug, and the 5-gallon jug has to be 4 gallons to defuse a bomb, right? Uses TLA Plus to solve this problem. Few preliminaries, and then he studies transaction commit, two-phase, Paxos, plus the AB protocol. Every recording takes usually like 20 to 30 minutes. But this is kind of like only video time. If you watch this, you will have to pause, you will have to rewind, you will have to do the exercises. So every video likely translates into a few hours. But don't be discouraged because of that, right? This is just, I mean, I think at this point, I can just watch them in real time because I know TLA+. But people who learn TLA+, they will need more time than just this 22 minutes here. Because this is fundamentally different from what you do usually in programming. This is a completely new concept. But I can only say that after doing TLA+ for many years, it really has changed the way how I think about systems. I now think in terms of invariance. What always has to be true. I have this vocabulary now available to me to better reason about systems. I know what liveness is, what safety is, and so on. This has really made me a better engineer, even if I don't write TLA+. So I think it's worth the effort. Other questions?